morning all.
Morning.
So we are a bit late today, so we will push all the sessions by 10 minutes and you will have a lunch break which is shorter by 10 minutes.
John, are you okay with that?
No. I'm coming back at 2:10.
I don't know if anyone noticed in the principal's only day on the first day.
Yes.
Did anyone notice? We said, be on time,
Or
otherwise go take
take
a
a
walk.
stroll.
Yes.
In the
Yes.
sunlight. Sunlight.
Oh no, that was be prepared or take a sunlight.
No.
That's the
Come,
story.
be here on time.
But in the handout, it was be prepared or take a sunlight.
We have to produce the documentation because the witnesses say we have to
Be
produce.
prepared or take a walk in the ice.
Okay, so I'll start with where I left you all the other day. Okay, so we did this, right? I just left you with this. I folded, then I folded this way, then I did this, and I did this, and they fitted properly. So why did I do that?
To show that
Huh?
the vertices of a triangle, the sum of the angles of a triangle is 180.
Okay, to show that sum of the angles of a triangle is 180. Did I prove it?
No.
No.
We don't know.
Huh? You don't know. Here it is. Yeah, this is fitting. So I proved that the sum of the angles of a triangle is 2 right angles
Of this
enough
triangle.
for a
of this triangle.
Of this triangle. Yeah.
So did I prove it?
No. No.
No. So what have I done here?
You showed a pattern.
Huh? I have just shown in a.
Demonstrated.
Something pretty
Okay, now you all also did this. It's not just me. If I did, I might have done some voodoo there and done this. But you all convinced yourself of the fact that this is happening. So we had 30 odd people here doing this, and every single one of them found that this was fitting. So that constitutes a proof.
No, conjecture. By
That
your
does-
terminology, right?
There may be one guy.
It was not conjecture by my terminology. What was it by my terminology? Does that convince you to a certain extent that this is so? Yeah. So what method of proof was were we using when 30 of us did this, and each one of us found that this was fitting, and we used the method of scientific proof. And I said that I am not happy with scientific proof. I need a mathematical proof. So what we are going to do today is a mathematical proof of this. So in the process, I also intend to convey to you the nature of mathematics. A couple of weeks back, I was talking to an 8th grader. I asked her, what are the things you like about learning? She said, I like maths. So I said, what is it about maths that you like? So she told me, I like to get more and more new formulas. I like to put in values there, calculate and find answers.
Yes,
Huh.
stop for a little while because
Yeah.
it's distracting. So wait for a little while.
Okay.
So,
No, it's in right, it's on there. Even when the light is not on.
Okay. So this girl told me that what she likes about mathematics is that she wants more and more new formulas into which she will substitute values and find out, do some calculations and find out the answer, whatever. So that is not mathematics. That is number crunching. So my aim, or our aim, in fact, I will do part of it, Madhav will pick up from where I left. Our aim is to give you a taste of what real mathematics is like. So we did a little bit on that day. We started out with, observing patterns. We made a conjecture. We made an attempt to prove it. We distinguished between scientific and mathematical proof. So we started off on day before yesterday or 12th or whatever. And now we are continuing that journey. Could have continued on that day, but then in between there was this murder in Boscombe Valley. So Sriparna had to investigate that. So she did it. In a way, what she did helped me. She had, this was a kind of, if you notice what she was doing, she had her grounds, she had assumptions, and based on these, she did some kind of reasoning to arrive at conclusions. Now, I am going to do something similar. We had a taste of this when we did the proof for angles and property of polygons. We had a little bit, and then she went into detail as to how to do that. And now I am picking up from where she left and getting back to the same thing in a little bit more of depth. So what were her grounds? Sriparna's grounds were the things which she observed, right? And what were her assumptions? Her assumptions were observational generalizations. Yesterday also you did the same thing. You made some observations when Anjali gave you that scale, and based on those measurements which you made, you came to an observational generalization, and then you go on to prove that. So the assumptions were observational generalizations, and from these you used reasoning, you used various types of reasoning, deductive reasoning, inductive reasoning, whatever, to come to the conclusion. Now in maths, also we follow a similar structure. We have grounds which I will just call as axioms or postulates and definitions. We will come to this later. What these are, I will come to it at the end of the class. Assumptions, these are my assumptions. Beyond this, mathematicians generally don't make too many assumptions. They make a handful of assumptions, but not more than that. Though that may not be the common view of mathematics. Yeah.
Are you saying that observational generalizations and assumptions are same?
Those, see, when Sriparna did the thing, she said that there was the imprint of a large foot. And then from there was a statement which said a large footprint would come from a tall person, or a tall person would make a large footprint. That a tall person would make a large footprint is an observational generalization. How? You look at the footprint made by a number of people.
I think the doubt might be because sometimes it's not necessarily explicit observational generalization. I mean, it's an observational generalization you might have formed.
Yeah,
I might be implicit, you may not even be aware.
out of your
Yeah.
In that
experience.
sense.
Yeah. Okay, so
Was that the question, or your question, or was it, do you have observation generalizations as the grounds in mathematics?
No, that was my question. I mean,
Which
are
one?
the two words same or they carry different meanings?
What was the question?
The question was, is observational generalization same as assumption or are they
Oh, I
different?
see, okay.
Yeah.
Right.
So in maths, the grounds are my axioms and postulates. And like I said, mathematicians don't assume too much. We assume a very minimum number of things. You have that handout which has been given, where you have certain things defined. I have not given the entire definitions. I have just given the definitions which we will be using in this class. And you have certain postulates. These pretty much constitute our grounds. You don't have anything else. With these, how many do we have? 6 and 5, 11 statements. You are going to build up a lot. So that's what we will be doing here now. So the assumptions we don't have in maths, and when the way we draw conclusions from the grounds and assumptions is purely by deductive reasoning. We don't use all the other forms of reasonings which you went through in the last 2 days. So now, with that, let's start on the proof for the angles and property of a triangle. Okay, before this, when we have grounds, assumptions, and conclusions, we are arguing for the conclusions given the grounds. Okay, so let me use. Let me say that given a set of premises. Grounds and assumptions for Sriparna were her premises. Okay, starting from the premises, you come to some conclusion. So you build an argument from the premises to the conclusion. We did it that day when we had the angle sum property of polygons, we did that. So when we came from the premises to the conclusions, there were two types of problems which we faced. One was that we said that there are n vertices for the polygon, and we said we will draw some lines, and then we said those lines would divide the triangle into, divide the polygon into n minus 2 triangles. So we were not clear how that this thing, we said okay, there are n minus 2 triangles, and we had to go into like the reasoning as to if there are n vertices, we will get n minus 2 triangles was not very clear. Our premises were there, but how we arrived at the conclusion that there will be n minus 2 triangles was not clear, and we went into the thing that if there are n vertices, we cannot draw to the adjacent one, we cannot draw this, so we can draw from n minus 3, so n minus 3 can be drawn, so we built up an argument for that. So sometimes there can be, okay, now how am I going to prove this mathematically? Give me the proof. I have a triangle. I have 3 angles. I have to prove that the sum of these 3 angles is 2 right angles. How am I going to prove that? The mathophiles. This is a proof which is done in the class 7 math textbook.
You just draw the line, draw perpendicular.
Huh?
You draw a line in between, draw perpendicular.
Huh? And
So then each of them are at 2 right angles.
which are the 2 right angles?
And that's how you prove that the sum of the angles of the two. These are 2 right angles.
I have to show that this angle plus this angle plus this angle is 2 right angles. How am I going to do that? Yeah, sometimes for proofs in maths you may have to draw these extra fitting lines.
Are we allowed to use external angle sum property? So to
You can use it.
Yeah.
yeah.
You can use it. Huh.
So just to take that approach further,
Huh.
say 2 right angles, and
Ah.
the sum of the 2 right angles is 360. You have to necessarily
180.
subtract 2
2 right angles.
two triangles, sorry.
2
So your
triangles.
2 triangles is 360.
So what is it that you are doing? What is it that you are doing? How do you know that? How do you know that the sum of the angles in 2 triangles is 4 right angles? I will draw. To give you this thing, I will draw a line.
That is exactly what we are trying to prove.
I will draw a line passing through this vertex and parallel to the base. I will need to name all this A, B, C for ease of writing the proof. Okay, so I will draw a line passing through this point and parallel to this. Can I do that? Are you convinced that I can always do it? I was able to do it here. Okay, anyway, go on. Now, from here, what do I do?
Here we all assume Euclidean geometry. Right?
You assume Euclidean geometry.
Is that line?
So you assume Euclidean geometry. If you assume Euclidean geometry, you have these many assumptions which you can use and nothing more. Anything beyond this, you need to prove. I gave you that theorems which are proved just to give you a taste of what are the kind of things which we ask proof for. A plane angle can be bisected. What does that mean? If you have an angle like that, you can divide this angle into 2 equal parts by drawing a line. A finite straight line can be bisected. If you have a line segment of some length, this can be divided into 2 equal parts. even things like this, which seem so very obvious to you, need to be proved. You just have this much stuff to start on.
So, can we use other theorems like alternate angles? And
You use any theorem that you want, but I will question. Okay.
Is that line that you've drawn?
Ah.
So angle B would be equal to that angle.
Name 2 points on that line.
Should I name 2 points or
On the
is
line
this
above.
It's enough.
enough? Is this enough?
C would be
Okay.
equal to
Okay.
2
Huh.
and B would be equal to say 1.
I mean, you are saying that these two are equal to 1.
C and 1 are
Okay,
equal.
I will put C as
Okay, 1 and 2.
Why don't we just
You
call
have
it
to prove that, no?
alpha?
No, that's allowed. Alternate angle.
Alternate angles.
No, why?
That angle.
and this angle.
Why?
Huh?
You have to prove that, no?
You have to prove.
Yeah.
Okay. So let me first write down the proof. Let me first write down at this level whatever it is that you're talking, and then you start questioning. Okay. So first thing that I did is
Very easy, yeah. This question.
given a line. Can you see the font size is a little bit small?
It's okay.
Huh? Huh?
You can see.
Where is the button for magnifying?
We'll zoom
Can you make it 24 font size? Because the camera is also here.
I need to write a lot. So given a line, so I will use short forms and a point not on it. There exists a line parallel to this and passing through this. Parallel to the line and
BC.
passing through the point E. Okay, let me call this as 1. This is an assumption that I am making. Though it might seem obvious to you, I said you are free to assume only whatever is there in that sheet which has been given. So I am assuming that given a line and a point not on it, I can draw a parallel line is an assumption which I am making. Okay, then what did you say? Then you said that given a pair of parallel lines, can you state that out? Who said? Prayas?
Yeah.
Huh. Given a pair of parallel lines,
the alternate angles.
the alternate angles are equal. Any questions there?
We require
John said you have to prove that before using it. Fine. Any other question? Huh?
if we are accepting that, then it is self-evident why it is 180. I mean, once we accept that alternate angles are equal,
Huh.
then it is very easy to conclude that it is 180.
Okay, we'll come to that. Even in this statement, given a pair of parallel lines, the alternate angles are equal.
Transfer.
Do you have any?
What is an alternate angle?
What is an alternate angle? Then
Alternate angles formed by a transversal.
alternate angle. Okay, given a pair of parallel lines, alternate angle you want to make it as formed by a transversal. So what? Are there any more questions?
Then what is it?
Are equal. What are parallel lines?
What is a transverse?
What is a transversal? So you have to define. Okay, we have accepted the definition of parallel lines as a pair of lines which when extended to infinity or extended infinitely, they don't meet. That is the definition of parallel line that we are accepting. Okay, now you know that parallel line, that was one definition, that if I have a pair of lines, to whatever length I produce, they do not intersect. That is a definition of parallel lines that I accept. Now, once I accept this definition, if you tell me that parallel lines are those lines where the distance between them remains a constant, that is not acceptable. You can't, play around with this. If you have to say that parallel lines are the pair of lines which are at the same distance from each other, you have to prove it. Anything that you say beyond what is there needs to be proved. Okay, so now let's take the definition of parallel lines as those that do not meet when produced indefinitely. And transversal, we are defining transversal to be the line which, actually if a line falls on a pair of parallel lines, a pair of alternate angles that are formed are equal, and we define alternate angles to be, one below this and this. There are ways of defining it. I will not get into that kind of definition right now, but it can be defined. You know what that alternate angle is. Okay, now given this, what? Next step. And this is something which we are assuming. Assuming as in this is an already proved theorem. So before we use this, we need to write out a proof for this. We'll do that in a step-by-step way. Now 1 and 2. Now if we have this statement 1 says that these two lines are parallel, and you actually have to write there that AC intersects both these lines. Which are the lines? BC, and let me call this as some line L. So given that these two are parallel and that this is a transversal, and that when a transversal falls on a pair of parallel lines, the alternate interior angles are congruent. Given this 1, 2 and 3, you can conclude that the angle 1 here is equal to the angle, see there I am not writing very precisely, and angle 2 is equal to the angle B. Yeah? Okay, now what is the next step? Now given this, what can you do?
Straight angle.
So you have a straight angle there. Angle 1, 2 and 3 make what you call as a straight angle. What is a straight angle?
Two right angles.
Two right angles. Okay. The definition of a right angle, if you look at that, is when you fold a straight line in such a way that both the angles formed are equal, you call that as a straight angle. So now here, can you show me that this thing out there is equal to two right angles? You have to show that. A straight angle is two right angles, which is a definition which we are using. So now, given that a straight angle is two right angles, you have this angle out there. Yeah.
The parallel line itself means it's a straight line, right? And a straight line means we have two right angles. Is that not a axiom or a definition that on that we have?
What was that? What was that?
A parallel line is a straight line.
Huh.
And if it is a straight line, then there are two right angles. And that's how we define right angles. So now, why should we go back again and try to prove that? That is the definition on which we have worked on.
We said that if I fold a straight line in such a way that both the angles are equal, each angle is called a right angle. That is the definition that you have. Now we are saying that this plus this is two right angles.
Oh, you cannot say that it all forms on the straight line, so it is.
So
The sum is 180.
two right angles. Okay. Okay. So it's a very small little proof there, just to convince ourselves that this is indeed two right angles. Okay. So you will use that and say that the sum of the angles is two right angles. Let me write that. Given that straight angles, we will write sum of angles in a triangle is two right angles.
But the
Okay,
important
no.
thing is to recognize it is not,
Huh?
it is a theorem.
Which one?
That theorem, what you're writing there is still a theorem. That's the way
Yeah,
we
this
wish
one
to
is a
point
theorem.
out.
This is not something which we have proved. That's exactly what I told Vignesh.
Yeah,
That
that's,
you just have the definition for right angle, and from there you're doing a one-step, two-step reasoning to come to the fact that your definition of right angle is, I will write this, definition of right angle is I'm not writing it. You have it there. If you have a straight line which is folded in itself, and if this is equal to this, then each is a right angle. That's what you have. Now, if you have a straight line, what you are telling me is what is called as linear pairs are supplementary in the textbooks. Okay, if you have a line and if another line falls on this, you are saying that these angles which are formed add up to 2 right angles. That's what you are telling me. Essentially it is the same, but strictly speaking, you need to draw that. So if I draw this, this tells me that this is 2 right angles. Now this right angle is this part plus this part and this. So this plus this is the same as this plus this, and therefore you come to the result that linear pairs are supplementary. That straight angle is 2 right angles, but you can't use it without proof. You need to get to this proof. Fine? Yeah.
No, I'm still wondering why. Two things. One is, by definition, you're drawing this, you have a straight line and you said a straight line is 2 right angles, right?
Definition is of a right angle. The definition says that if I have a straight line and I fold it in such a way that the angles formed overlap, then each angle is called a right angle. That is my definition.
And
Now,
do you also say that the straight line has got 2 right angles?
I'm not saying that.
Oh.
I'm not saying that. My definition is, if I fold a straight line in such a way that both the angles overlap, each angle is called as a right angle. I'm creating a concept called right angle and I'm defining it. This is how I'm going to make a right angle. Now, here we don't have right angles to say that this is 2 right angles. So, you draw. Now, whether I can draw, given a line and a point on it, I can draw a line perpendicular to the line passing through that point. It's something which seems obvious to you, but even such things need proof. It's a theorem in Euclid that given a line and a point on it, you can draw a line perpendicular to the given line through the point. This is what I am using here to prove that this is 2 right angles. So you will need to prove this. Am I getting across? Okay. Huh?
See, everything that we know we have to prove, it looks like. But it's difficult for me to see as to how you go about defining what needs to be proven and how do you go about proving it.
What needs to be proven is, I have given you a list. Anything other than this list needs to be proven. This is like building up a house. You know, you have some building blocks. You use those building blocks. Maybe you have some Lego blocks or something. You have certain basic block types. You combine those things to make some entity. In the process, you may combine 2 or 3 to make one big thing. You may combine that with another one to get another thing. So this is something like that. You start with a set of building blocks which is minimal. I'll come to what should be the characteristics of those building blocks. Madhav will also pick up on that. So you have a set of postulates or axioms and a few concepts which you have defined, and these are the only things that you have. Now combining these, you build up your world. So, okay, so this, I think because some of these things we are so used to accepting that when we ask for a proof, it kind of, unsettles. And some of these things, this very basic things, when we get into the proof, it might seem to you that why have such a convoluted proof, we might as well accept. So we will come as to why mathematicians don't do that at the end of the thing. Okay, so now this one, that a straight line is made up of 2 right angles is something which we prove. In the proof of that, we use the fact that given a line and a point on it, there is a perpendicular which you can construct passing through that point. So this part is done. As in, this assumption that we made is already proved. Now, what are the other assumptions that we have made?
Alternate angles are equal.
Alternate angles are equal. So let me write that down. And how are you going to prove it? The statement is given a pair of parallel lines and a line that falls on them, a pair of alternate angles are equal. You have a pair of parallel lines, and this is how the define alternate angles. Now you have to show that given that these two lines are parallel, you have to show that these two angles are equal. How do I go about doing that?
Draw a perpendicular from E to CD.
Draw a perpendicular from E to CD. Yes?
So when we say perpendicular, it means we have
Yeah.
two
These
right
two are these two are right angles. That is by definition. Which forms a triangle? Okay. EF. Okay, I will name that point G. EFG is a triangle.
Could you draw it a little bigger than
This one?
Yeah.
Any thoughts? The maths teachers here. Today I am calling upon the maths teachers to prove. Yeah. This is something which you would use every day. And have you questioned why it is true?
So while proving this, we are assuming that the last thing which we prove, sum of
No.
straight lines,
You cannot assume. You cannot
straight
assume
lines,
that.
two right angles.
See, this is something, this is a bigger block which we have built up using this smaller one. So when proving this, if you use this, it goes into a circle. You use whatever is there in the sheet which I have given. You may have to use some other theorem. If you use some other theorem, I will ask for a proof there also. I think, okay, I need to, that is a theorem. Okay, so if you do that, you need to prove it. No, this I gave you this as a sample of things which have been using.
I mean, not that it's
So if you use this, you need to prove that. So just because I have put it in here, doesn't you can use only if you use this, think of a proof for that also.
So we have proved that the straight line is 180.
Yeah, you can use that. You can use, see, here when I wrote out the proofs here, I use the fact that pair of parallel lines when a transversal cuts the alternate interior angles. So I am going to prove it now. I use that, given a line at a point not on it, I can draw a line which is parallel to that. Now after I prove this, I will have to prove that also. Okay, here I want to demonstrate a method of proof which we use in maths, which Mo also referred to yesterday, proof by the method of contradiction. Okay, so what do we have to prove? We have to prove that this angle is equal to this angle, right? This is what we have to prove. Now, contrary to what we have to prove, let us assume that angle AEF is not equal to EFB. We have to prove that they are equal. We assume that if possible, let them not be equal. Okay. Now, what happens if they are not equal? One of them is greater. If they are not equal, you can pick out one of them as the greater one. Which one do you want to pick as the greater one? Anyone? Okay, so let me say, let angle AEF be the greater. Mind you, I can do the same thing if I assume EFB is the greater also. It's not going to make any difference. Now, let AEF be the greater one. This is my greater one. Okay, so I will write that angle AEF is greater than angle EFB. Now to both sides, I will add this angle BEF. So I can BEF.
So it's the whole thing.
Whole thing. I don't need that. So if I add this same quantity to both sides of this inequality, the inequality will still remain, right? So I can write angle AEF
That again requires proof.
plus which one?
Adding the same angle.
No.
That is obvious. That actually is listed as a common notion in Euclid, saying that equals added to equals gives equals, whatever. So angle AEF plus which angle did I add? FEB. Angle FEB is greater than angle EFB plus angle FEB. Okay, this we will take it without question. Now, AEF plus FEB is this, right? So that is two right angles. We have proved this now. We have proved this. So I take that this is two right angles is greater than angle EFD plus angle FEB. So EFD plus FEB are the interior angles on the same side of this transversal, right? Just for a little bit of this thing, I'll give you the definitions. If you have a pair of lines cut by a transversal, mind you, I said pair of lines, I didn't say parallel lines. A pair of lines with another line falling on that. These two angles, we use the term corresponding angles. This and this we call alternate angles, and this and this we call as co-interior angles or interior angles on the same side of the transversal. So now here you have the sum of the interior angles on the same side of the transversal is less than two right angles, right? Sum of the interior angles on the same side of the transversal is less than two right angles. What does the postulate say? Which means these two lines will intersect somewhere on this side if I extend them. Now I said that these lines are parallel, and my definition of parallel is that to whatever distance I extend this, they are not going to meet. So there is a logical contradiction, which is something which I cannot accept. So it means that this particular assumption that I have made, where did it come from? I said I had to prove a certain proposition Q. I assumed not Q. Okay, and I came to P is my, I claimed that these two lines are parallel, which is my proposition P, and from there I said if parallel I needed to prove that the alternate angles are equal, which is my proposition Q. I assumed not Q and I ended up with what? Not P, which means this particular thing, the assumption that I made is not true. So, which means that the alternate integral angles are equal. That is the proof there. Yeah.
You still use the property that co-interior angles are supplementary.
I have not used co-interior angles are supplementary. Read the fifth postulate which is written there. Fifth postulate
itself is,
huh?
I mean, it is a postulate presently. But
yeah, but for
it is a postulate presently. It is a postulate based on which Euclid built his world.
oh, so
It is a postulate based on which Euclid built his. If I don't like that postulate, I am free to pull it out and build my own world with the remaining 4 postulates. Or if I want to add another postulate there,
so this is an axiom.
it's not an axiom, it's a postulate. See, the thing is that I am building out a. You are
I
going.
don't think it's worth doing the distinction between axioms.
Yeah, I think we can treat.
Assume it's an axiom.
Yeah, doesn't matter. For this purposes, you can use the word axiom to cover both.
Okay. So, see, I start with a set of axioms and I build up a world. Now, fifth postulate has been problematic. There have been people who said that, looking at the simplicity of the first 4 and I don't want to accept this, they tried to prove this, whatever. So, if people try to pull out the fifth postulate, substitute it with something and build up another world. So that world is also perfectly valid. You are starting with a different set of building blocks and you are building a different world. You are not talking about this particular world which we inhabit. Based on certain building blocks, you are creating your own worlds. It's up to you. What are the building blocks that you assume? It's up to you the kind of world but given the building blocks, they will create a certain kind of world. You cannot have logical contradiction.
Yeah, it should not have logical contradiction.
So there is a certain kind of world which will emerge depending upon the kind of building blocks that you take. So,
Just for knowledge, has there been another world created? I mean, apart from this, using not the fifth postulate?
Yeah. One form of the fifth postulate. This is also another form of the fifth postulate. That you can prove. I was supposed to prove this now, right? This was the other assumption that we made. Given a line and a point not on it, there is a line passing through that. This is what we call as an equivalent form of the fifth postulate. That means if I assume the fifth postulate, I should be able to prove this. So now if I prove if assuming this, I will be able to prove the fifth postulate. Now this tells me that given a line and a point not on it, there is one and only one line which passes through this and parallel to this. Now pull this out. Okay, you think of the surface of a sphere. On the surface of a sphere, we define a straight line as the shortest distance between 2 points. So on the surface of a sphere, the straight line, I will not use the word straight line, the line, straight line, it comes out to be the great circle on the surface of the sphere. Great circle means something like the equator, which divides the sphere into 2 equal halves. Now take a line on the surface of a sphere and a point not on it. Now can you draw a line which is parallel to this line and passing through that point? Can you draw such a line?
It depends on the notion that line means it should be straight, but here it can be...
Line I said is the shortest distance between 2 points. So on the surface of a sphere, you can't go inside the sphere. You are bound by the surface of the sphere. So on the surface of the sphere, a line is a great circle. So if you are given a line, a great circle on the surface of a sphere and a point which is somewhere, this suppose is my sphere and this is my straight line which is the great circle, and if I have a point there which is not on this, can you draw another great circle, that is another line, which passes through this and does not intersect this, that is parallel to this?
Yeah.
Can you?
Yeah.
How? Draw.
Same way.
This is not a great circle. Great circle means it has to splice the sphere into two halves.
You want a great circle, another great circle.
I want a straight line. By my definition, the straight line on the surface of a sphere is the shortest distance between 2 points, which works out to be the great circle. Can you draw such a line?
No, I don't get that.
Straight line is defined as the shortest distance between 2 points. See, I have 2 points. I can draw any number of lines. But what is it that I called a straight line? It is the shortest distance between these two. Now I abstract this definition of straight line when I am on a spherical surface. So I define a straight line as the shortest distance between 2 points.
But these 2 points can be anywhere. Why are you thinking it's on the greater?
Take it anywhere. Take it anywhere.
But it has to be on the surface.
It has to be on the surface.
Of the sphere.
On the surface. So if you take any 2 points on the sphere, say you take from India to say Philippines, you can't go through the, so it has to be on the surface of the earth. So you will, there are many, many paths which you can take. The shortest path will be the path of the great circle that passes both through say Pune and Philippines. Okay, so if that is what the straight line comes out to be, and if you have a point which is not on that, can you think of another great circle which does not intersect this and passes through this?
No.
You can't. Which means the fifth postulate is violated there. Fifth postulate says that given a line and a point not on it, there exists a line which is parallel to this and passing through this. You pull this out, and that's how spherical geometry came. If you are on a hyperbolic surface, you can show that there are infinitely many lines which you can draw. So that is a different world. Euclidean world is a different world. The world of spherical geometry is another different world. Okay.
Jayashree, so there was a question that Shmikant asked. If I remember right, he said that in the course of this proof, you used something other than the postulate. I'm not quite sure what it is, but yeah.
What have I used?
Kind of implied, when she said I realized, it kind of implied that interior angles in the last two statements, from second last to the last statement, it implies that interior angles are supplementary, but it doesn't directly say that.
Okay.
So I'll go back.
It's fine.
I got your point. I drew attention to the fifth postulate for that.
Yes.
Fifth postulate says that this is what it is. Okay, so now do we have any assumptions which we need to prove in this? I think I can stop here.
No, I have a question. When you said that straight line is the shortest distance between 2 points, if we talk in terms of time, it would imply that the shortest amount of time taken to arrive from point A to point B is the same. Right?
That need not be the same. I mean, the shortest distance does not mean the shortest time.
There could be traffic.
Yeah. That's what.
Can you go to that left hand side and sort of make sure that everything on the left hand side, the first one,
First one.
and make sure that everything has been proved.
No, this has not been proved. I can give the proof, but looking at their faces and whatever message I had to convey has already been conveyed. Now I know that, see, if I look at the first one, I said given a line and a point not on it, there exists a line parallel to it passing through this point. I can prove that. This is something which we have not proved yet. We can prove it. Then we say that given a pair of parallel lines, pair of alternate interior angles are congruent. We proved that, and we said that a straight angle is equal to 2 right angles, which also we proved, though I don't have it neatly written out there. We proved that. Now the next step would be to prove this. Or in this, have we used anything any other thing which you want to question. If we go through this proof, the only thing which we used here is the fifth postulate, that if the angles on a side is less than 2 right angles, they meet on that. That has been accepted without question. So here we didn't run into any problems. Now I can prove, if you want, I can prove this, but I think I have got across whatever it is that I wanted to convey.
So just the moral of the story is, if you question a conclusion in mathematics, which is a theorem, then you have to give a proof. And if the proof contains theorems, then you question those, and you keep questioning those. Ultimately, you end up with axioms and definitions which cannot be proved. That's the moral of the story. And in a similar manner, if you do the same thing to science, you end up in what we yesterday saw, the subjective experience, and which cannot be, which are not subject to proof. Those are the foundations. Foundations means no further proof is possible. In mathematics, the foundations are axioms and definitions where no further proof is possible, but you keep digging. That's the moral of the story.
And one more thing, like you asked, okay, can I use, you wanted to use the exterior angle theorem to prove
If we
it.
use that, then we don't need to prove this part.
You don't need to prove that. But how will you prove the exterior angle theorem? You are using the exterior angle theorem.
So using the sum of angles of a triangle is 180 and a straight line is 180, we can prove that sum of interior opposite angle of a triangle is equal to exterior angle.
You wanted to use the exterior angle property to prove that the sum of the angles in a triangle is 180. Right? That was your position.
Assuming that.
No, assuming that this has been proved.
So you can't like, to prove this you use exterior angle property, and to prove exterior angle property you use angle-sum property of a triangle. It only means that they both are equivalent. You have not given a proof for it. So if you are using exterior angle property to prove the angle-sum property of a triangle, which can be done, you should do that without using the angle-sum property of a triangle. There are other ways of proving exterior angle property. I will give you a handout in which the whole thing is done, like going back to the axiom. So he's telling, yeah, I have had it. Okay. So that's it. Yeah.
Some sense of how understanding of this at this level would be useful for a school student?
For a school student, I told the example of an 8th standard school student who said that for her she likes math because there are a lot of formulae and she can substitute values and calculate and find out more and more this thing. So if that is what she likes, and if she goes on to study maths further, and if this is what she sees, she is done for. And there are people like Madhav here who will do this well, but if you give him numbers and formulae, he is totally lost. So for a child who is in that 8th to 10th stage, if she has to decide what it is that she wants to study further, she should know what that discipline is about. Without knowing that, you cannot decide, okay, what is it that you want. There are people who fancy these kind of things and there are people who don't. So you have to have at least a basic understanding of what the discipline is.
And but it also adds
Even-
a sense of
even if-
rigor.
huh?
It also puts in a sense of rigor into you.
Yeah.
Where you're questioning every single thing and you're asking for justification. Because not just in here, because you would take this outside of mathematics as well, and ask for justifications for various small things which you wouldn't ask for otherwise.
Also, purpose of school education, if we look at it, 10 years if you are in school, you should know a little bit about what all the disciplines are. You should have an understanding of what goes on.
In this last one,
Huh.
in any triangle, if one of the sides is produced, so is it something like what you've drawn there?
Yeah, he used something more than that.
But
In fact,
something if the angle is obtuse in the triangle.
That is obvious. That reason is exposed to this.
what that says is, if I extend one side, the angle that I get here is greater than this and greater than this. What he says is something stronger. This just says that this is greater than this. The exterior angle property says that this is equal to the sum of these two. And this being an
because it's 180 minus x.
Huh?
It is 180 minus the other one. Both of them are 180 minus the third angle. Yeah.
So if we go by proving corresponding angles are equal, by the fact that vertical angles are equal, and then prove alternate angles are equal.
You can do that. You first prove that corresponding angles are equal.
Yeah.
In that
but
proof,
then we have assumed that.
no, we have not assumed. We have not assumed. I proved this just because we used the alternate angle property there. If I had used the corresponding angle property, I would go about proving that. So to prove the corresponding angle property, I will require vertical angles are equal. So I will prove that. And then come to this. So the handout proof which I have given, it has both the things, like corresponding angles, vertical angles. I'll give it to you by the end of the day. So
the definitions and postulates are what we assume to be true. They are the basic, what we are accepting. And based on that, we prove these theorems or not. So we cannot assume any
no, you cannot assume any of those theorems. Okay, now one question I have. I said if we assume something, we can use that. We can assume everything, no? we can assume 100 theorems and 135 definitions and create a world on that. What is wrong in it? What is wrong in it?
Basically that principle where you go to the minimum possible, and then you see that there are no logical contradictions. That is what the balance.
And the prediction also should correspond.
Exactly. So you choose your set of axioms in such a way that you have a minimum number of axioms. There is no logical contradiction, which means if you assume a set of axioms, you should not be able to prove a statement and its contradictions. You have this set of building blocks. If it is possible for you to prove P and not P based on this set of axioms, there is something wrong with that. So you should have a set of axioms from which you cannot prove logically contradictory statements. You should have the minimum number, and from that minimum number, you should be able to generate the maximum number of theorems. So that is what is called as theory, mathematical theory. The individual things which you prove are your theorems, and your set of axioms and definitions along with the bunch of theorems that you prove is what is called as mathematical theory. Theory has got different meanings in science and maths. So this is what you call. Madhav will do more on that.
Regarding what Mo said about ultimately you come to certain grounds which are both there in maths and also in science. So which we cannot question, or we are not able to certain those axioms. So then it also means that science has that limitedness.
So does math.
So does maths.
Both,
so scientists, those who claim that science is foolproof, or it's equated with the truth, it's a perspective of truth which can be. I mean, the way we know about it, we do not really know whether we.
No, I think the scientists who say that they are giving us the objective truth do not understand science.
Yes, so that's what many scientists claim that.
And I would in fact go on to say they are not scientists.
Vignesh, you had to say something.
If we have time, otherwise I can reserve it for feedback. It's the time.
Okay. I just want to close with one small point. I started out with the angle sum property of a triangle which is there in the textbook. Okay, and I wanted to drive back to the axioms. If my intention had been making you understand the subject matter, I wouldn't have dropped my thing at this stage. Because my intention is to take you through all this. You have to understand the proof for given a line and a point not on it, there X is a parallel line, I will use something else there. You have to understand the proof for that. You have to understand, so many other proofs. So I will take you through the entire set of proofs. That was not my aim. My aim was not giving you content knowledge in maths. My aim was something else. Certain things about maths I wanted you to understand, which happened through the discussions even before I completed the entire set of theorem. So I stopped there, though you have not gone through the content area of the remaining proofs. One common question which we are facing is, what is the difference between inquiry based and inquiry oriented? Now here, the proofs I gave myself, these proofs I started off, it was something of an exposition. So the inquiry as such, you did think about it. I'm not saying that you didn't think, that was there, but still it was largely an exposition mode with certain aims in mind, which was not content related. So I just want to point out the difference between what we are doing.
वो कैमरा we'll have to wait 2 minutes.